Hi, welcome back. Today we're going to talk about the types of energy, how they're transferred from one form to another, the different units that they take in chemistry, and how to work what we call heat problems. Let's get started. Okay, so the first thing that we want to talk about is what is thermochemistry, which is this section. So that's the study of the transfer of energy as heat. In the form of chemicals, and then we turn it into either kinetic energy or potential energy, chemical potential energy, or vice versa. Temperature and heat. There are differences between those two things. So temperature is the measure of the average kinetic energy of the particles in a sample of matter, whereas heat is the energy that is transferred between the samples of matter. And you can tell the difference between the energy that one sample has versus another sample by taking its temperature. So the temperature is really the indication of how much energy a sample has. Heat will also always flow from a high temperature to a low temperature. So I think we've talked about this before. There's no such thing as cold. There's either heat and then less heat or more heat. All right, so let's talk about what heat capacity is, or more commonly known as specific heat. So the chemistry definition for specific heat is the amount of energy required to raise the temperature of 1 gram of any substance by 1 degree Celsius. A calorie may be a type of energy or a unit of energy that you have heard of before, obviously, when you're looking at nutritional facts on the back of anything that you would buy in the grocery store. And it lists the calories that substance contains. So for example, I have the nutritional facts for 1 can of Coke listed on the screen now. And it listed as 230 calories. However, those 230 calories are actually what we call kilocalories, okay? Because it's listed with a capital C. And if we have calories listed with a capital C, those are actually kilocalories, which means that 1,000 regular calories are equivalent to 1 kilocalorie or 1 capital C calorie. So this 230 here, that's 230 kilocalories, which is really 230,000 regular calories. Another type of energy unit that we might talk about would be joules. And this is the SI unit. This is what's used in every science class. And that says that 4.184 joules is equivalent to 1 lowercase c calorie, 1 regular calorie. The definition of a calorie is the amount of energy required to change the temperature of 1 gram of water by 1 degree Celsius. So the definition for specific heat and calorie is really, really similar. The only difference is that specific heat is talking about any substance, whereas calorie is talking about water. Okay, so energy is the ability to do work or produce heat. And you'll talk more about work when you take physics, so we're going to kind of leave that one as it is for now. Okay, so there are 3 main types of heat transfer. We have radiation, conduction, and convection. So radiation is going to be transferring heat by an electromagnetic wave. Typically, we think about getting light from the sun. That would be a transfer of energy from the sun to the earth through light. That would be visible light, that would be UV light, that would be infrared light. All of those forms would be transfer of energy through radiation. And that transfer of heat through radiation doesn't need any material or what we call a media through which to travel. That light wave travels through the vacuum of space. It doesn't need air molecules or metal or anything like that to get the energy from the sun to the earth. Electromagnetic waves can transfer their energy without needing a substance to pass that energy along. So touch is not required for transfer by radiation. The next type of energy transfer we're going to talk about is conduction, okay? Conduction is transfer of energy through touch, and that means direct contact. So if you were to, touch a handle of a pot that you left on the stove, and let's say that handle is made out of metal. Remember, metals are conductors. They are good at conducting heat and electricity. So if you touch that metal, it's going to conduct that heat into your hand, and you could get burned. Or if you ever had like a lesson from the fire department in elementary school when you were a kid, maybe they came to elementary school when I was a kid, and the fire department told us, how we detect a fire in our homes, even if it's at night, and what we're supposed to do and all this. And you're always supposed to have your bedroom door closed at night, because that offers a barrier in case any other part of your house catches fire. It won't immediately spread to your bedroom. And so if your fire alarms go off in the middle of the night and you go to your bedroom door, instead of just reaching down and touching the handle of your doorknob, you're supposed to put the back of your hand close to the doorknob to see if you can feel any heat coming off the doorknob. If you were to just touch the doorknob immediately and there was fire on the other side of the door, it could burn your hand. And the way that it would do that is through conduction. It would be conducting heat into your hand from the doorknob. So that's another example of conduction. Convection is the last example of heat transfer, and this one is done by movement of molecules of a fluid. So that would be a liquid or gas, because both of those are fluid. In this case, no touch is required, and it would transfer heat by moving molecules. That's why we said put the back of your hand near the doorknob, because all the air molecules around the outside of that doorknob would be receiving energy from the doorknob, okay, because they're touching the doorknob. So they're going to increase their temperature, they're going to increase in energy. And then if you move your hand near the back of the doorknob, those same molecules of air that now have extra energy, they're going to be moving around your hand. The back of your hand, and they will conduct energy into your hand that way, and you'll be able to detect that increased temperature because those molecules have an increase in energy. And so we want you to detect the heat through convection rather than conduction, because it's not as efficient in its transfer of energy as conduction is, because that's direct contact. All right, let's talk about a heat curve of water. Now, every substance is going to have its own particular heat curve, and it will generally look like this heat curve. So I'm just going to kind of break this down for you. On the y-axis, we have temperature, typically in Celsius, but it could be Kelvin or Fahrenheit. And then on the bottom, we have heat added. Sometimes it says energy added. Sometimes it says time. And so as we increase heat over time, the temperature is going to go up. That's why there's a positive slope to this graph. Now you'll notice that there are there's a couple of sections here where it kind of plateaus. This is when you're changing state of matter, okay? So in these sections where you can see there's a positive slope, we're changing temperature, and where it's horizontal here, where it's plateaued, we're changing state. So you're going from solid to liquid, and then liquid to gas. So that's what's happening here. It is not possible to change temperature and state of matter at the same time. Can't do it. So let's say that we were starting with water, and the temperature of that water is something less than 0 degrees Celsius. So we would be down here. So we have a solid, it's ice. Let's say the ice is negative 15 degrees Celsius to start with. Well, as we add energy, that temperature is going to start to increase until it gets right here. This is 0 degrees Celsius. At 0 degrees Celsius, the ice, is going to start to melt and change into liquid water, okay? So right here on the y-axis, this is 0 degrees Celsius. Then after all of the water, every single molecule of water has changed from a solid to a liquid, then we can go back to increasing the temperature, because we've been adding energy the whole time. That whole time we were adding energy, and then eventually we get everything melted, and now that energy can go back into increasing the temperature. So the temperature goes up and up and up and up until we hit this point right here, at which point we're going to start changing the water from liquid water into gaseous water, or steam. So we get all of it changed into steam. And at this point right here, this temperature is 100 degrees Celsius. So over here on the side, that's 100 degrees Celsius. Okay, so right here, we said this was 0 degrees Celsius. And then up here, we said this was 100 degrees Celsius. Okay. And then after this point right here, the energy that we add is just going to make the gas molecules have a higher temperature because we've changed every single molecule from liquid into gas. All right, now a couple of values that we need to know over here in order to be able to work some problems later on. The heat of fusion, okay? When something fuses, that means comes together, okay? So down here, the heat of fusion, in other words, the energy required to change a sample from a solid into a liquid or a liquid into a solid, that's called the heat of fusion. And for water, it's going to be 80 calories per gram, okay? And then we have the heat of vaporization, to vaporize, to turn something into a gas. So to go from a liquid to a gas, or to go from a gas back to a liquid, that's going to be this heat of vaporization. That's 540 calories per gram. You should know both of those values, okay? And then specific heat. The specific heat of water when it is a liquid is 1 calorie per gram degree Celsius. And the specific heat of water when it's a solid or a gas, that's 0.5 calories per gram degree Celsius, okay? So we need to know these values in order to be able to do some calculations here in a minute. Now, you'll notice that I said for heat of fusion to go from a solid to a liquid, or a liquid back to a solid, or for the heat of vaporization to go from liquid to gas, or back from a gas to a liquid. Well, these values change very subtly depending on which direction you are moving in. If we are talking about continuing to add heat, then that means that we are adding heat to the substance the whole time. And if it's adding heat to the substance, we have this positive slope, okay? And in that case, that means that we have an endothermic reaction going on. We have an endothermic system. So we're having to put energy in, so that we have this positive slope. And in that case, these values here would be positive numbers, positive 80 calories per gram and positive 540 calories per gram. However, if we are removing heat, okay, we're taking heat out, then in that case, that's an exothermic reaction. If you're losing heat, exo, exit, okay? And so if we're losing heat, then we're gonna have a negative slope to our graph, okay? So all of the heat is being lost in this case. We're losing energy. And so in that case, these numbers right here would need to be negatives, okay? So it would be negative 80 calories per gram or negative 540 calories per gram. So depending on which way you're moving up the heat curve, either you're moving in this direction up the heat curve or this direction down the heat curve, you would need to either use positive or negative numbers for that. Okay. So let's say that we want to work a problem, all right? It's called a heat problem. First thing we need to know is what the heat curve looks like. So we'll have to be able to sketch a heat curve for a different sample, whatever it happens to be. We should stick with 1 unit of energy the entire time. So either calories or joules or kilojoules, kilocalories, whatever. I prefer us to use calories and then switch to joules at the end because water has really nice round numbers. in calorie form, right? So it's like 1 or 0.5. That's way easier than using 4.184, which is the decimal number. So I like to do calories first and then convert to joules at the very end. Make sure that you are aware if you are working up or down that heat curve so that you can decide if the numbers are going to be positive or negative. And then you're going to add up all of your sub answers to get your final, total answer. Okay, so let's look at the next page here. Let's do a practice problem together. All right, so this one says, how much energy is required to change 50 grams of ice at negative 15 degrees Celsius into steam at 125 degrees Celsius? Write your answer in joules. Okay, so the first thing that we need to do is sketch out our heat curve, okay? So this is just a rough sketch of what the heat curve would look like for any substance, no matter what it is. But because this said the substance is water, we know that this is 0 degrees Celsius, and we know up here that this is 100 degrees Celsius because this is specifically water, okay? And in this first plateau, we're going from a solid to a liquid. In the second plateau, we're going from a liquid to a gas. All right, so now we can go about starting to map out exactly where we're at. So it said that we're going to start at negative 15 degrees Celsius. So we can say, okay, right here, that's going to be our negative 15 degrees Celsius. And it said that we are going to go to 125 degrees Celsius. So I know that negative 15 is lower down here because this is 0. If this plateau represents 100, then 125 is something above that. So we're going to say, all right, we're going to go to 125 degrees Celsius up here somewhere. Now, you can't just immediately go straight to 125 degrees Celsius. You have to map it out in little sections. Because remember, we said it's impossible to transfer or to change temperature at the same time as you're changing state. So that means that our very first section is this section right here, where we're going to go from negative 15 degrees Celsius to 0 degrees Celsius, and we're going to stay as a solid the whole time. So this is what's called a change in temperature. So we're going to use a change in temperature formula, which is Q equals M for mass times Cp, the specific heat at a constant pressure, times delta T. That triangle right there stands for the Greek letter delta, and that delta means change, okay? Change, final minus initial, okay? Delta means the change or the final minus the initial. So it would be our final temperature minus the initial temperature. Okay, final minus initial. Q is energy, all right? That little Q there, that represents energy, and because we're talking about water, it's going to be easier for us to put things in units of calories, and then we'll change it into joules at the end because that's what they asked for. Okay, so we're going to say Q equals, the mass that they gave us was 50 grams. Okay, so we're going to put our 50 grams in here. And then we need the specific heat. Now, at this point, this location down here, that is when the water is a solid, when it's ice, okay? So remember that the specific heat of water when it is a solid or when it's ice was 0.5 calories per gram degree Celsius, all right? So 0.5 calories per gram times degrees Celsius. And then we need the delta T, the change in temperature, final minus initial. Well, the final temperature that we're going to end up at is the 0 degrees Celsius, okay? The initial temperature that we were at was negative 15 degrees Celsius. So 0 minus negative 15 is positive 15 degrees Celsius. Okay, so we need to figure out what this value is. We're just going to plug this into the calculator, 50 times 0.5 times 15, and we get 375. Now we need the unit, okay? Remember, we said earlier that units of energy are going to be calories, joules, kilojoules, kilocalories, something like that. So we should automatically know that it's going to be calories, but we can prove that by doing a unit analysis, looking at our units. I have grams in the numerator and I have grams in the denominator, so that cancels out. I have Celsius in the numerator and I have Celsius in the denominator, so that cancels out. That leaves me with calories in the numerator, so that's the unit for this one problem, or this one section of this problem. Okay, so that brings us up to the point where the water is going to be a solid at 0 degrees Celsius. And now we need to change it to a liquid still at 0 degrees Celsius. That's this next little section of the graph here. So we're going to change from a solid to a liquid, but we're going to stay at 0 degrees Celsius the whole time. So in this case, it's not change in temperature anymore. Now it's change in state. So we need a new equation, a new formula type. By the way, this up here is called the change in temperature formula. And right now, we're looking at the change in state formula. So that's going to be mass times the heat of either fusion or vaporization, depending on what section of the graph you're in. Okay, now for us, we are using the heat of fusion at this point because we're going from solid to a liquid. We're not vaporizing anything. Nothing is becoming a gas or coming from a gas. So we're going to use the heat of fusion. So that says that Q is equal to the mass. You can't create or destroy matter, so we still have 50 grams of our ice. Now it's ice at 0 degrees Celsius. So 50 grams times the heat of fusion for water was 80 calories per gram. Okay, 80 calories per gram. So now I have gram in the numerator, cancels gram in the denominator. That's going to leave me with calories. So I'll type that into my calculator. I'm going to have 50 times 80, and that's going to give me 4,000 calories. All right, so we've got 4,000 calories at this point, and that puts us now where we have liquid water at 0 degrees Celsius. So now we want to do the next section of our heat curve, which is going to be to change from liquid at 0 degrees Celsius to liquid at 100 degrees Celsius. We're changing temperature now, so we want to do our change in temperature equation. So that's this one up here, mass times specific heat times the change in temperature. This one here, that one's our change in state. Okay, so we can say Q equals, the mass is still 50 grams, the specific heat. At this point, we are liquid. The water or the substance is now liquid water. So the specific heat for liquid water was 1 calorie per gram degree Celsius. And then that last one was delta T, the change in temperature. So that's going to be the final temperature, which is 100, minus the initial temperature, 0. So we have a change of 100 degrees Celsius. So that's going to be 50 times 100. So here we'll say Q equals 5,000 calories. Okay. All right, so that gets us up to the point where the water is a liquid at 100 degrees Celsius, and now we want to do the next section where we change it into a gas. So now we're right here and we're going to get a gas at 100 degrees Celsius. So we need to use the change in state formula. So we'll say Q equals, we still have 50 grams. And now we need to do the change in state. And this time we're going to go from a liquid to a gas, which means we're vaporizing. So we need to use the heat of vaporization. That's the bigger number. So that's going to be 540 calories per gram. And then we can plug that into our calculator. So we'll say 50 times 540, and we get 27,000 calories. Okay, so at that point, we now have gaseous water at 100 degrees Celsius, and we just need to do the last section where we transform it into gaseous water at 125 degrees Celsius. So that means we're doing a change in temperature this time. So we're going to say Q equals the mass, which is 50 grams, times the specific heat of this substance. At this point, the substance is now a gas, okay? Right here, the substance is a gas. And when water is a gas, then we need to use the 0.5 calories per gram degree Celsius as our specific heat, okay? Because when it is a solid or a gas, it is 0.5 calories per gram degree Celsius. So we'll put that in here. And then finally, our delta T, final minus initial. So we're going to go from 125 degrees Celsius to, as our final stopping point, minus 100 degrees Celsius is our initial point. So that means it's a 25 degrees Celsius difference there. Okay, so then we'll just plug that into our calculator. And we get 625 calories. And at that point, we have finished the requirements of the problem, right? The problem said that we want to convert it into steam at 125 degrees Celsius. And that's exactly where we've ended up here. It's in the gaseous state at 125 degrees Celsius. So we did it. We've gotten our individual amounts of energy that it took to do all of these steps along the way. And so what we want to do is come back through and add up all of these individual amounts of energy, okay? So let's do that real quick. We got 375 plus 4,000 plus 5,000 plus 27,000 plus 625, and I get Q is equal to 37,000 calories. All right, but the problem didn't ask me how many calories of energy this would require. It asked me how many joules of energy it would require. So I need to do a little dimensional analysis, okay? So I'm going to put my given over 1. So I'm going to put that 37,000 calories over 1. And then I'm going to make sure my unit matches top and bottom. So calories is going to go on the bottom so that whatever unit is on the top matches with the unit on the bottom. And we know that 1 calorie is worth 4.184 joules. Okay. So we'll take our 37,000 and multiply it by 4.184, and that is going to give us 154,808 joules. And then, of course, we need to pay attention to sig figs. So up here in the problem, we've got 50, we've got negative 15, we've got 125. That 50 right there, that only has 1 sig fig because there's no decimal point. That means we can only have 1 sig fig down here on the bottom. So here's the first sig fig. We look at the next place value over for rounding purposes. that means we have about 200,000 joules of energy required to make this conversion from ice at -15 degrees Celsius into steam at 125 degrees Celsius. Okay, I hope that that was helpful to you. That's just this one little section of our thermo notes, and we will continue with our thermochemistry notes in the next lesson. Thanks for learning with me today. Bye.